Okay, so let's talk about electric current. Okay, so let's see. Charges can move. So you can imagine basically a tube of some sort, and you can put some charges in here. Q, 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 and these charges basically can flow along the tube. All right. The rate at which charges move, you can imagine basically the rate is equal to a certain number of charges that move through some region divided by the time. This will just be the change in the number of charges, basically the number of charges over the change in time. This is defined as I, which is the current. Okay, and if we ask what's the units of current, I has units. Of charge over time. So this is Coulomb over second, and this is given a name. This is called ampere, right? Or A for short, right? A lot of people, I mean, if you're in your house and you look at the rating of something, amps basically means ampere, right? Now, the convention is that positive charges move, okay, that's the convention. Reality is that negative charges move. Okay. Namely, the negative charges are electrons. Okay. The reason why that this convention is that when electricity was first discovered, you can have either positive charges moving, negative charges moving, and they decided to just choose positive charges to be the ones that are moving. Right? Operationally, it makes no difference either if it's negative or positive charges that are moving, right? But it's just basically people made a guess, and unfortunately they guessed wrong. Right? It's fine though; it works out exactly the same. Right? So as this current moves, as the current flows, right? It encounters resistance. Right? Okay? And to overcome the resistance, right? You need an electric field. Now this electric field can be either strong or weak. Basically in stuff that which doesn't conduct electricity easily, it's actually very strong. In stuff that conduct it can be actually pretty weak. But in stuff that doesn't conduct electricity, it needs to be actually pretty strong. Okay. So what that means is that suppose you try and move some current over some distance here. So supposed to move some distance L. There's a current that needs to be flowed, and this is charges Q, 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 Q. But there's some resistance, right? And so to basically do that, you have to maintain electric field here. Okay? And so basically between point A and point B, all right, there's going to be some potential difference, right? So you can compute basically what the potential electric potential at point A is, electric potential at point B, and these will not be the same, right? So basically, over a distance L, right, you will see a potential drop. Right? What is this potential drop? Well, that's simply going to be V is going to be equal to VA minus VB. It's going to be basically E dot L, which is going to be basically V here, right? Okay. So we can define resistance as R is equal to V over I, right? And it's measured in okay, so this is over volts over amperes, right? I is amperes, this is volts. And this is called something called ohm, right? And it's denoted by this omega, capital omega here, right? Greek capital omega. Alrighty, all right. So this thing here actually is a very classic law, right? So basically, R is equal to V over I, or V is equal to I times R. All right, this is called Ohm's law. Okay, so the amount of energy dissipated across a resistor R is, okay, so let's see, so let's figure that out. So we basically drew this picture here, right? There's this V between this two, a V, okay? And so the change in energy, potential energy, is equal to minus V dq. So what that means is minus, you divide by d by dt, du dt is equal to V dq dt, right? But you know that is, this is just I, so it's equal to V times I, right? Right. So expressing in terms of resistance, this means that the power is equal to, this is essentially the power now, is equal to, using Ohm's law, either I squared times R, or is also equal to V squared divided by R, or it's also equal to V times I. Okay. Right. Okay, so to maintain a current, right, we must apply electric field, as we say earlier, but what that really means, we must apply a source of voltage. Right. So basically, this is known as a EMF, which stands for electromotive force, right? And this is basically typically a battery. Okay. All right, and this supply EMF is represented by epsilon. Okay, that's basically a symbol epsilon. All right, so we should talk about basically resistors and circuits. Okay, so basically again, there are two types of circuits. Right, there's basically if you're going from basically A and B, right, you guys have put things in series. Oops. This is a series. Right. Okay, or you could put things A and B in parallel. Yeah. Right. And this is a symbol usually with R in front of some value is a resistor. Okay. Now, suppose now we have a current flowing through these circuits in series and in parallel, right? Current I flowing in series and parallel. Okay, so let's do the series first. All right. So in this case, what we have is that we have this thing, then this thing again, right? And then I just flows through the entire circuit, right? From A to B. We can basically attach a voltmeter here to measure the voltage across that. Likewise, we can imagine some current basically flowing in parallel. Okay, so I comes in this way and then splits into basically I2 on the bottom and I1 on the top, and comes out again to be I. Oops, sorry, nothing else there. And in this case, you have a condition that the current I is equal to I1 plus I2, right? Okay. Okay, and if we measure the voltage here, we'll measure some total voltage basically. This will measure that if you apply some voltage, this will be basically measure some V. Right. Okay. And likewise, if you have basically, let's call this R1, R2, R1, R2. Okay. All right. So what that means is that in this case, if I put a voltmeter here and another voltmeter here, okay, in this case, what I end up getting is that the total voltage I measure is equal to V1 plus V2, the voltage across resistor 1, voltage across resistor 2. Right? This is basically the rule for series. And this is simply going to be the current flowing through voltage resistor 1, that's I times R1 plus I times R2. Okay? All right? And so if you think about it, basically this is equal to I R1 plus R2 V. I could replace it with an equivalent resistor, right? So for instance, I could replace this one with some single resistor with the same sort of measurement, right? Get I flowing this way, R equivalent, right? And this is here is R equivalent, right? So what you're getting in this case for series is that R equivalent is equal to R1 plus R2, okay? Plus dot 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 if you want to have more, okay? Likewise, in parallel, all right, basically you can measure two voltages across this way, okay? And in this case, V, the voltage measure from these two terminals, is equal to V1 equals V2, right? And each of these is just in turn, basically, this is equal to I1 R1 plus I equals I2 R2, right? And also we know that I is equal to I1 plus I2, right? Okay? And so, basically in this case, right, this statement basically implies that I2 is equal to, well, you just divide it out, I1 times R1 over R2, okay? Right? And then you take this thing and put it in here. This is basically I is equal to I1 plus I1 R1 over R2, right? And so you can compute out what I1 is. This is I over 1 plus R1 over R2, right? And I also know that basically V, which is equal to V1, is equal to I1 R1, so using this term again. And this is going to be equal to R1 I divided by 1 plus R1 over R2, okay? So again, I could replace it with some equivalent resistor, I flowing here. This is R equivalent. And so if you write this thing out, this is I R1 over 1 plus R1 over R2, okay? This is R equivalent, right? Now that's an ugly way of writing it. It turns out there is an easier way of writing this thing out. Let's back to what this thing looks like. R equivalent is equal to R1 over 1 plus R1 over R2, okay? So could we write this as 1 for R1? 1 over this thing implies that 1 over R equivalent. This is a normal way of writing it. 1 over R1 plus 1 over R2 plus 1 over R3 dot dot dot. Okay? Now, if you recall what we got for capacitors, basically, capacitance is C equivalent, so okay, let's compare to capacitors. Okay. So in that case, for series, parallel, okay, capacitor, resistor, okay. So in series, if you recall, basically 1 over C equivalent is equal to 1 over C1 plus 1 over C2 plus dot dot dot. For resistor, is R equivalent is equal to R1 plus R2 plus dot dot dot. Okay. In parallel, the equivalent capacitance is equal to C1 plus C2 plus dot dot dot. And in parallel, the equivalent resistance is equal to 1 over R1 plus 1 over R2 plus dot dot dot. Okay? All right? So they're basically just opposite of each other, right? Okay. So let's do some simple examples. All right? So first simple example we're going to do is basically a 3 in series. R. Okay, what was this? It's all connected series. R equivalent is equal to R plus R plus R, right? It's equal to 3R. Okay. Let's do it in parallel now, okay? 1, 2, 3. Okay, this is R. 1 over R equivalent is equal to 1 over R plus 1 over R plus 1 over R. This equals 3 over R, which implies R equivalent is equal to R over 3. Okay, number 2. All right. So now, let's do one more. Okay, we'll do this in parallel. Okay, pen is gone. And then do another one series. R. Okay. And in this case, let's do this part first. This is 1 over R equivalent is equal to 1 over R plus 1 over R is basically 2 over R. So that means that R equivalent, I call this 1, say, is equal to R over 2. And now, this is the same as doing, that's this resistor here again. And this is R equivalent. So R equivalent, 1, is equal to R equivalent 1 plus R, which is R over 2 plus R, which is 3/2 R. Okay? Pretty simple. Alrighty. Okay. So now, this is like some of the tools that we need to build up circuits, all right? And we introduce something called Kirchhoff's law. So we can do all kinds of complicated circuits, right? Or Kirchhoff's rules. So let's do. I think, I see, slightly off, that's why. Okay. Kirchhoff's rules. Okay. All right, so suppose you have a complicated circuit. One page on. All right. We have a complicated circuit. All right. I'm going to draw something out here that looks a little bit complicated. Whoops. And then there's another one. And then let's say there's a parallel plate capacitor there. There's something else there. And another parallel plate capacitor. And this is my complicated circuit here, all right? The question is, how do you solve such a circuit? All right. Now, we're going to start with one thing here, all right? Let's imagine I put a voltmeter in this little corner here. Okay? So if you put a voltmeter at a single point, okay, you're going to measure the voltage. That's going to exactly give you 0. There's nothing in between, right? So the voltmeter has to be 0. Okay, so that's, but there's something interesting. I can imagine I'm measuring the voltmeter at this single point, or I'm measuring the voltage as I go around the entire circuit. All right? So those two statements are equivalent. Measuring this voltage at a single point is the same as going around the entire circuit. And so that basically gives the first Kirchhoff's rule. The voltage drop across a closed loop is 0. Okay, first rule, right? Okay. Part of it is that I decided to pick some direction. So the 0th first Kirchhoff's law is you want to draw an orientation for the circuit. Okay? So pick directions by which stuff will flow. Okay? Okay. I forgot to show this. This should be a battery here. Okay? I'll put an E epsilon here for the EMF. Okay? Okay? And I believe this is a minus and a plus. The big plate is a plus plate. Okay? So, as part of this rule, let's make sure I get all these rules and numbers and all that other stuff correct. Okay, would you like this? Okay, now 2. Okay? Let's say you go across the battery. So going across the battery, from minus to plus gives a plus epsilon, minus epsilon otherwise. There's only 2 directions, right? You can go from this way or you go that way, right? If you go that way, going from plus to minus, you can pick up minus epsilon. If you go this way, basically from minus plus, then you pick up an epsilon, right? Okay, 3. Okay, so now suppose I draw some orientation. I'm going to basically say that I is flowing this direction now, all right? Okay, now if I go across this way, then what happens is that going across the resistor, picks up a minus IR, right? If going in direction of I. All right, so I picked up orientation of I. I'm going in the same direction. I pick up minus I. I pick up a minus IR. Okay, right? Plus IR otherwise. So for instance, if I pick the orientation this way and I go backwards on this way, I'm going in opposite direction of IR, because I'll pick up a plus IR in that case. Okay. All right. Now, I'm gonna write this thing down. We'll do it for resistors for now, and then we'll let me just make sure I have everything correct. Yes. Okay. All right, write number 4 here. Okay, going across a capacitor in direction of I picks up, well, let's see, what was V for capacitor? Well, V is equal to Q over C, and so in this case, it will pick up a plus Q over C, right, minus Q over C otherwise. This last rule is going to be important later on, but for now, we're just going to basically include it, right? And last but not least, right, I should write down one last thing. Number 5, this will eventually not be number 5. Add it all together. Per loop to give 0. Okay? All right, so we won't do capacitors this time, but, we will do, let me see, we will do a little capacitors later on, right? But for now, we're just going to consider just resistors for now, right? Okay, so these are Kirchhoff's rules, right? The 0th order rule over the 5th rule, okay? Let's basically apply it to see how it works. Okay, so I'm going to start with a very simple example here. I have basically a battery here. I'm going to pick it going, there's my resistor. And I'm going to tell you what the resistance here is. It's going to be 2 ohms. And this is going to be 6 volts, right? Okay. So this is epsilon, right? This is R. Okay, so let's go through all the different rules first, right? So let me just get that rule again. So first, 0th order rule, draw orientation for the circuit, right? So I don't know any better, the plus minus. I'm going to basically draw I in this direction, okay? That's the first thing to do, okay? Okay, the voltage drop across close to 0, okay, that's great. Going across the battery from minus plus and plus to minus gives a plus epsilon or minus epsilon other way. So what that means is that I should pick a point which I'm starting. I'm going to start, I usually like to pick the lower left-hand corner, right? So I'm going across the battery. So once I go across the battery, I pick up a, let's see, plus 6 volts, plus 6, right? Okay, next thing. Going across the resistor picks up a minus IR. So going across the resistor, there's my resistor. I'm going into the direction of I. So it picks up a minus I times 2, right? That's R. And then going across the capacitor, the capacitors, I don't have to worry about it. Add it all together per loop. This is a per loop. Add it all together equals 0. Okay? And now we go ahead and solve it, right? So we basically this thing solves. I is equal to 3, and let's get the proper units, amps. Okay? Right. Now, this is not the only way I could have done it, right? I could have done it like this, right? And in that case, I'm going across this terminal right here. This will be basically a minus 6. Actually, sorry. Let's go. So if we start here, go this way. That gives me a. I'm in the direction I. That's a minus I times 2. Going back, going across the battery in the opposite direction, that's a minus 6 equals 0. And in this case, I is equal to minus 3 amps, right? And that makes sense. This minus sign denotes the direction that I chose the direction to be counterclockwise, but this minus sign means I'm opposite direction. Well, actually, the current is flowing in the clockwise direction, right? So it all works out, basically, as long as you basically follow it all very systematically. Okay, so let's do a slightly more complicated example, right? So I'm going to draw this one, looks like this. Another one. Okay, I'll give this thing a value 2 ohms. 3 ohms. I'll put the same 6 volt battery there again, right? And now I have to be more careful, right? So let's see. So 0th order rule is that I have to draw orientation. Let's do that. Orient everything this way. This is I. Okay. And so when it goes here, all right, I got to do something, which is I have to split up the current. So I need to add to my rules 6 at forks. Okay. I in equals I out. All right. Okay. So I'm gonna draw my orientation first. All right. So I'm gonna call basically this one I1. This is I2. Right. Okay. And technically this is gonna be I4. All right. So at this fork here, what comes in is I. This is equal what goes out, which is I1 plus I2. Okay? And similarly at this fork right here, what comes in is I1 plus I2, and what comes out is I4. Right? So basically the first thing we get is I is equal to I4. All right? Okay? That's not surprising at some level. Okay? Now let's go and draw our circuit. Sorry, so I'm going to start lower left hand corner. I have to do 2 different loops. I'm going to do 1 loop here, and then the second loop I'm going to do is I can basically go and do this entire outer loop like that. Right? Let's go and do that. So let's go here. So I start to say go across this thing. So basically this is the plus sign. So I go in the direction is basically epsilon, which is 6. Now I'm going to go through this inner loop minus the first one is going to go in direction I2 times 2 is equal to, coming back to the same point, 0. Okay? Now let's do the outer loop. Then basically that one's 6, going across this way, going across this one, minus I1 times 3 equals, coming back, 0 again. Right? And then I have this rule as well. Right? Okay? So what that means is that I2 is equal to 3 amps, I1 is equal to 2 amps, and I, which is I1 plus I2, is equal to 3 plus 2 equals 5 amps. All right? So that's basically all there is to it. Okay. All right. So that's the beginning of Kirchhoff's law, right? Let's talk about even more complicated example, right? Let's see now. Right. Okay. So I'm gonna basically draw this one out now. I'm gonna draw, another more complicated one. Okay. This is 2 amps. 2 ohms. This is 3 ohms. But now we put another battery there. 2 ohms up here. I'll put the 6 volts here. Put a 12 volt battery there. All right. And then I'm gonna pick basically 2 different loops. I'm gonna draw my orientation first. Let's draw this orientation. I'll call this I1 now. All right. And then here, this would be I3. I2, okay, and then this would be I4, going this direction. All right. So that's and I'm going to basically do 2 loops here. I'm going to do 1 loop like this. That would be loop 1. Now the second loop like this. That would be loop 2. Okay. I'm going to start here for the first loop and start here for the second loop. All right. So let's go through this one. Okay. So I'm starting this point. Go across it in the positive direction. That gives me a positive 6. Going back this way, down to here. That's a minus I3 times 2. Close up, equals 0. Now let's do the second loop. I start here. I go up, but I'm going in the opposite direction of I3. So this would be a plus I3 times 2. Going across I2. Going this way, minus I2 times 3. Now this is a plus sign, and I'm basically going in the opposite direction, the minus 12. Closing it back, equals 0. Okay? Now let's look at the different points here. I1 is equal to in equals out, I2 plus I3. And then let's look at this point here. What comes in? I2 plus I3 is equal to what comes out? I4. And so this thing gives you I1 equals I4. Right, first thing. All right, so let's go solve the rest of it. This means that I3 is equal to 3 amps. And this one right here, well, I figure what I3 is going to be, so this is going to be, let's plug that into there. So this one is going to be a 3 times 2 minus I2 times 3 minus 12 equals 0. 6 minus 12 is minus 6. And so this gives me I2 is equal to minus 2 amps, right? And so what that means is that it's actually flowing in this direction, right? I point I2 this way as long as I do that way, right? And so basically we're essentially done now. I1 is equal to, I2 was 3, no, sorry, I2 was minus 2, plus I3 was 3, that's equal to 1 amp, right? And so basically you have all here, this is 1 amp, this flows in this direction with 2 amps, and this flows down with 3 amps, right? And it all works out. Okay, beautiful. Okay, so we can do actually I'll skip the last couple of examples. I think at this point it's pretty clear what's happening. Right, okay. So let's talk about RC circuits. Okay. So, so you have a circuit like this, parallel plate capacitor, resistors R, okay? Okay, so at T equals 0, so initially we're going to place a plus Q and a minus Q here, right? At T equals 0, we shut the switch, across the circuit, right? And then the question is like, what happens after this, right? So let's basically draw this thing out, okay? So make sure I understand this one completely. Yeah, okay, let's just do it this way. Okay, so I'm going to draw my current in this direction, right? Okay, so the initial voltage here, right, was basically Q over C minus now, going across this one, IR equals 0, right? And so you have Q over C is equal to I times R. Now, I is equal to minus dq dt, because whatever flows through here is subtracting from the total charge which is being stored there, right? And so what this implies together is that Q over C is equal to minus R dq dt, okay? Right? Let's basically write this thing out in a more suggestive form, right? So what this would say is that I could rewrite this one as minus Q over RC is equal to dq dt. Okay, so I want to solve this equation here, right? So how do I solve that equation? Well, you could rewrite like this, right? So you can multiply by dt, bring the dq out on the bottom. So this is same as basically writing as dt over rc is equal to dq over q. Or now, all the q's on one side, everything else on the other side, right? So now you just integrate everything, okay? And so this is just, integral of this one is just t minus t over rc, okay? And this is integral of dq over q. Well, I know what that is. That's just the logarithm of q. So this is equal to the logarithm of q. Now, there's a constant here and a constant there. So we just group as one constant plus some constant. Okay? Which I don't know yet what the constant is, but we'll figure it out later, right? And so, basically, if this is true, okay, that means that q is equal to, you take the exponent of everything, this is equal to exponent of a constant, exponent of minus t over rc, right? Okay, technically it's a minus constant, but whatever, it doesn't really matter, it's still a constant. So this one, I'm going to basically call this as another constant right here, I'll just call it a, exponent minus t over rc, okay? So now you need to know one thing, right? So at t equals 0, well, there is a charge q0 on the capacitor, right? So let's plug in t equals 0. So q at t equals 0 is equal to q0, which is equal to a exponent minus 0 over rc. Well, that's just, the exponent of 0 is just 1. This goes to 1. And so that place a is equal to q0. And so we're left with the solution. Q of t is equal to q0 exponent minus t over rc, right? Okay. Now, we can write this as q is equal to q0 exponent minus t over tau, where tau is equal to rc, is called the time constant. Right? Okay, and because basically you have a resistant capacitor and RC comes in this combination, these are known as RC circuits. Okay, so when this happens, we are discharging capacitor. Let's call about discharging capacitor. We already determined basically that Q of t is equal to Q0 exponent minus t over RC, or t over tau, okay? And so if you plot this thing out, it's a function of time, Q, it starts out at t equals 0, at Q0, and it exponentially decays off, right? So this goes like exponent minus t over tau here, right? Okay. So, what happens to the voltage drop? Okay, well, the voltage across the capacitor, well, that's just always Q over C. Well, we know what Q is. That's just that right there. So it's Q0 exponent minus T over tau. I'm going to write it as tau to save my hand a little bit. Divided by C. And so it's going to be Q0 over C exponent minus T over tau. Guess what this is? This is just the initial voltage at time t equals 0. That's V0. Okay? And so this would be V0 exponent minus T over tau. Okay. Okay? And the current? Well, I is minus dq dt, right? So it's basically minus d by dt of q0 exponent minus t over tau, all right? Which is equal to, you take a derivative with respect to this thing, you get a minus, which now is going to be a plus, q0 over tau exponent minus t over tau, right? Or equivalently, you could write this as q over rc exponent minus t over rc. Okay? Two ways of writing it. Okay. So that's basically discharging capacitor. Now you could do another example, which is you could charge a capacitor. Right? So let's draw a circuit for that one. That looks like this. So now we're going to need a battery here, okay? And then open the switch, put a resistor there, put a capacitor there, put a resistor with resistance R, put capacitor with capacitance C, plug this in, plus sign here, okay? Okay, and I'm going to draw my circuit here. There's my I here for this direction, okay? And so epsilon, so I'm going from this point, I pick up the epsilon here, plus epsilon, minus, okay, so let's say at t equals 0, close switch. Okay, so I'm going to minus IR here, I go across the capacitor, minus Q over C equals 0, right? Now, in this case, you got to be a little careful here, right? I is going to be flowing into this thing, and so in this case, basically, I is equal, I'm charging the capacitor, it's going to be equal to dq dt. Okay, I'm charging this capacitor now, right? Okay, so what we have is now, we have epsilon is equal to, epsilon minus dq dt times r minus q over c equals 0, right? Okay, so now to solve this equation here, all right? And this equation is not that easy, not that clear how you would solve it, right? So I need to do a substitution. I'm going to let x equals epsilon minus q over c, and then basically dx is going to be equal to, well, epsilon is some constant now, it's going to be equal to minus dq over c. All right? Okay? So if I write this thing out, this will give me so this is dx dt times r right? Plus, yeah, this is the right one. Let's see now, this is epsilon minus epsilon is plus x goes 0, right? And so that's the same as writing this as x over r with minus sign is equal to dx dt. Okay? So I solve the same way as I did before. Okay? Basically, I'll rewrite this again. X over r is equal to dx dt, right? this is the same as writing as dt minus over r is equal to dx over x. Whoops, I missed one thing. Of course, be very careful here. This is dq, dc. So there's a c right here. Good. Now it makes more sense. There's a c right there. Perfect. Okay. All right, and there's a c right here. Perfect. Okay, so now we can finish this off now. Okay. So now let's just integrate this thing again. So this is going to be my minus t over rc is equal to logarithm of x plus some constant, right? It's just basically the same thing as this is before, right? And that means that basically if I want to write this down, that this is basically exponent minus t over rc is equal to x times some constant. I'll call that basically a, right? So it's equal to a exponent minus t over rc. Okay. Now let's expand that what x was. So recall x is just this thing here. So this is epsilon minus q over c is a function of time now is equal to a exponent minus t over rc. All right. Okay. So I would need to know a critical piece of information, right? At t equals 0, q of this thing, I'm going to assume it's initially uncharged, right? Q of t equals 0 is equal to 0, right? And so if you plug this in, that means epsilon minus q of 0 over c is equal to a exponent minus t over rc. Okay, sorry, it's 0 again. So that goes to 1, right? This goes to 0, and so that means a is equal to epsilon, right? And so now we are done. Okay, we'll write this as epsilon minus q of t over c is equal to epsilon exponent minus t over rc. Let's simplify this thing out. Looks like this. Q of t is equal to c epsilon 1 minus exponent minus t over rc. Close everything out. All right. And now we can sort of plot what this thing looks like. Okay. Right. So plot q as a function of time now. At time t equals 0, you can work this thing out or know this is true. At t is 0, this is exponent 0, which is 1. 1 minus 1 is 0. So it starts at this point. And you pick some really late time later, t equals, let's say, infinity, that's exponent minus infinity is 0. So it basically becomes c times epsilon. So it looks something like this. And it peaks out at somewhere where it's just epsilon times c, or c times epsilon. Right? Okay. Okay. Let's see. Right. So let's go figure out basically how much work that it took to basically charge this capacitor, right? How much work did it take to charge the capacitor? Well, that's not hard, right? We know basically total charge plus move is Q, Q, right? And the work, right? Work is equal to integral of V dq, right? This Q is like essentially always constant, so this is going to be equal to epsilon times Q, right? That's the voltage, right? Okay, so that's the total thing, right? But interestingly, the energy stored is only 1/2 CQ squared, right? Which is, I'll call this V times Q, right? This is going to be basically 1/2 C times Q is just basically V, right? It's going to be basically Q times V. So there's a 1/2 difference between these two statements here, right? Okay. So where did the other half of the energy go? Other energy half, well, it got dissipated by the resistor, right? So in this case, basically, dW dt is the work done by the resistor, that's just the power. This is equal to I squared times R, right? It's one of our power rules that we stated earlier. This is dq dt squared times R, right? And so, if we look at what dq dt was, right? Well, it's basically dq dt is equal to this term right here, d by dt of C epsilon 1 minus exponent minus t over tau, just call it over tau, just to keep it simple. 1, 2, 3, right? This is just going to be a minus, that's a plus, C epsilon exponent minus t over tau, right? Okay. Divided by tau. So I forgot that. Okay. And so what we have is this dw of r dt is going to be equal to, okay, let's plug this term into there. So there's going to be a c squared epsilon squared, tau squared is just r squared c squared times r, exponent minus 2t over tau. Okay? So c squared kills this off, this kills one factor of r off, right? And so what we have is epsilon squared over r exponent right, that's correct. Exponent minus 2t over tau. Okay, so now let's integrate this with respect to time. Integrate with respect to time. And we integrate from 0 to t equals 0 to infinity, right? Because that's how long it takes to charge this capacitor fully, completely. All right, so this is just going to be equal to the work done by a resistor. It's just going to be integral t equals 0 to infinity, okay, of dt of epsilon squared over r exponent minus 2t over tau, right? You work this thing out. This will give you a minus 1/2 tau epsilon squared over r exponent minus 2t over tau, evaluate at t equals 0 and infinity, right? When you do that, this just gives you a 1 out here, and everything else just basically works out. So this is going to be equal to 1/2 tau is RC, so C times epsilon squared, right? okay, which is equal to 1/2 Q times epsilon, or Q times V, right? So that's the other half of the energy, basically got dissipated heat. So this is half the energy is dissipated by the resistor. Okay. Alrighty. That's beautiful. Okay. So I want to discuss one last thing for this lecture here. Okay. And this is just like some of the beauty that physics can sometimes give you. All right. Okay, so I'm going to discuss something which is just like a trick, but it's a very useful trick sometimes, right? And for those of you in computer science, it basically goes under the idea of recursion, right? So let me show you the trick. Suppose you have infinite ladder resistors, right? So it looks like this. Okay. 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 And this just goes on forever, basically, okay? And I'm going to give these things the same resistance, R, 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 okay? So, the question is, between these points A and B, what is the equivalent resistance, right? And so basically I want to find out between A and B what R equivalent needs to be, right? Okay, so let's just draw a simple one, okay? Let me imagine I look at this first loop here, okay? So I'm going to draw this first loop. Okay. All right. And I'm going to just map out what the rest of this looks like. So I'm going to map out here. What's the rest of this look like? Well, this is infinite thing. And so this one is also R equivalent, right? It's the same thing. Basically, this setup right here, if I just cut it off, it looks exactly the same, but it goes off to infinity, right? So this is R, R, and R, okay? So now, this is the key idea, right? So this thing will just recurse forever, essentially, right? And so, first thing I'm going to do, I'm going to basically write out what R equivalent prime is here, basically for these two things. I know what that is. That's R1 over R equivalent prime is equal to 1 over R, that's this resistor, plus 1 over R equivalent, which I don't know yet, okay, that one. And then these things connect in series, right? So this basically, I replace this one with 1 over R equivalent prime. R equivalent of between these two is equal to R plus R equivalent prime plus R again. So 1, 2, 3, all right? Okay? And so, if I expand this thing out, this is 2R plus, now, this implies that R equivalent prime is equal to 1 over R plus 1 over R equivalent. 1 over R plus 1 over R equivalent. All right? And then this is equal to R equivalent on this side too. So it's equal to R equivalent, right? So this is the form, this is the equation I need to look at in order to solve everything. All right? So let's stare at this for just a second. All right? And as you stare at it, you are, what's the right word? realize you could rewrite this one as, let's see, 2R plus, I'm going to bring the R equivalent on top. The cost of basically writing this as R equivalent over R plus 1. That's equal to R equivalent. Okay. Now multiply by this thing. So now I have basically multiply everything by R equivalent over R plus 1. Okay. And so this gives me 2R, R equivalent over R plus 1 plus R equivalent is equal to R equivalent over R plus 1. Okay. All right. So this is R equivalent squared over R plus R equivalent. Okay, good. This kills off one factor of that. This one becomes 2R R equivalent plus, 2R equivalent plus 2R is equal to R equivalent squared over R. Okay. And now let me make sure. Yeah, okay, so I always something wrong in my notes, and so basically this is easy enough to fix. I'm going to multiply this by R again. So that's R squared R, okay? And so this is just becomes a quadratic equation now. R equivalent squared minus 2R equivalent times R minus 2R squared, okay, equals 0. And so basically recall ax squared plus bx plus c equals 0. The solution is x is equal to minus b plus or minus square root of b squared minus 4ac over 2a. All right? And so a in this case is 1. B times x is 2r, and then c is 2r squared. All right, so let's go do that then. So this R equivalent is equal to minus, let's see, so this is a minus sign, but it becomes plus 2r plus or minus square root of 4r squared minus 4 times ac, so 4 times a is 0, c is minus r squared, so it's plus 8r squared, good, divided by, perfect, 2a, that's just 2, okay? So this is going to be equal to, basically, r plus or minus square root of, let's see, so this one is over 2, this is 12 r squared, okay? And so this is basically equal r plus or minus square root of 6r squared, right? So basically r times 1 plus or minus square root of 6, right? And in this case, there's 2 answers, but only one of them is valid, right? Because the R equivalent has a positive, and so the only one you can pick, you're forced to pick, basically 1 plus square root of 6, right? And so that is the answer for this one. All right, and so that concludes our lecture for this week. All right, we will discuss next time more about electricity and magnetism.